My name is Kevin Boos, and I'm a researcher from Rice University. Today I'm going to talk about Theseus, a new operating system we have created from scratch to experiment with the structure of and state management within operating systems, and also how we can leverage the power of modern safe systems programming languages while doing so. This work was done in collaboration with my colleagues at Rice and Yale University, Namatha, Ramla, and Lin. In this work, the key research hypothesis guiding our OS experimentation is whether fundamentally redesigning an OS to avoid state spill will make evolution and fault recovery of the OS components easier. And, as we began to build the system, a deeper question arose about how much modern systems programming languages and compiler-enforced safety can help. Initially, this line of work was motivated by a study of state spill from Eurosys of 2017, a phenomenon in which one software component harbors changed states as a result of handling an interaction from another component, such that the future correctness of those components depends on those changed states. State spill is quite prevalent in modern system software, and it leads to fate sharing between software components that are otherwise modularized and isolated, hindering the realization of several challenging yet desirable computing goals. Things related to availability, like fault isolation and fault tolerance or recovery, and things related to evolvability, like live update and maintainability, as well as other goals. Take a simple example of two applications interacting with an OS service. As a result of handling an interaction from app A, the OS service now holds states relevant to that client app A. Similar changes in the service state occur after interacting with app B. Both of these are state spill. Now, if the server crashes and then restarts, as is the default recovery procedure in most systems, those states representing the progress of app A and B's interactions with the service will be lost, or will be in an inconsistent state. This causes undefined behavior in the worst case and an immediate crash in the best case. For example, our study showed that state spill from applications into Android system services caused the entire user space frameworks to crash if a single system service fails and crashes, even bringing down applications that aren't even using that crash service. Similarly, reliable microkernels like Curious and Minix3, as well as live update systems like Proteus, also corroborate our findings by showing that server-held states pose problems for fault recovery and live update. Now, although we started building an OS from scratch to address state spill, we found additional motivation in modern systems programming languages. We were initially drawn to Rust due to its ownership model and compile-time memory safety, which bring clear benefits in an OS environment. And after experimenting with Rust for a bit, we realized that it can be leveraged for far more than just writing safe OS code, such as enabling the compiler to check certain correctness invariants for OS-specific behaviors and resource usage. In addition, we're further motivated by the two most important goals I previously mentioned, evolvability and availability, which require a lot of additional effort beyond just addressing state spill. These abilities are crucial in certain system software domains. For example, the embedded system software in spacecrafts like satellites, rovers, and probes, or in implanted biomedical devices like pacemakers, must be updated without any downtime or loss of context. Even in data center networks where switches are replicated for reliability, software failures and maintenance updates in the switches still lead to network outages, despite that redundancy. We believe that Theseus is well suited for these environments. Now, the outcome of our experimentation is Theseus, a new OS we've written from scratch in Rust that makes the following contributions. First, Theseus establishes an OS structure of many tiny components, which must all have clear bounds that persist into and throughout runtime. Second, it follows intralingual OS design, intralingual meaning within the language, in which we leverage the strengths of the Rust language to empower its compiler to take over common OS duties, such as resource bookkeeping and preventing unsafe or incorrect resource usage. Third, Theseus strives to avoid or mitigate the effects of state spill. Theseus has been designed and implemented with evolvability and availability in mind, and it currently consists of just under 40,000 lines of Rust code, split across over 200 crates. These contributions can be put more simply as the design principles that we follow. We'll discuss each one in detail. But first, let me give an overview of Theseus' structure. Every component is a cell, a software-defined unit of modularity that serves as the core building block of the OS, much like their namesake of biological cells in an organism. Cells are based on crates, which is Rust's project container that comprises its source code and a manifest file specifying its dependencies on other crates. To realize the first principle of runtime persistent bounds, we dynamically load all component cells within Theseus, not just drivers or kernel extensions, as is commonly done in existing safe language OSs and monolithic and microkernel systems as well. This enables Theseus to track and maintain the location in memory and the size of every cell, as well as their bidirectional dependencies on other cells. Then when loading and linking cells at runtime, we construct detailed metadata, as shown on the right, that tracks this information at section-level granularity. The set of publicly visible symbols in all of these loaded cells forms a cell namespace, which is useful to quickly resolve dependencies between cells during runtime linking. This metadata is also a crucial component of the key evolutionary mechanism in Theseus, cell swapping, which we also reuse for fault recovery. Now, more importantly, all Theseus cells execute in a single address space and privilege level, meaning that everything from top-level applications and libraries to low-level core kernel components are observable as cells. In turn, this enables Theseus to apply its single cell swapping mechanism uniformly to any cell, and also to jointly evolve cells across multiple layers safely. The second design principle is to leverage the power of language by enabling the compiler to check safety and correctness invariants to the fullest extent possible. Rust already provides a variety of invariants and built-in rules to ensure safety, such as its ownership model and borrow checker that ensure the lifetimes of references don't exceed the lifetime of the object they refer to, aka use after free. For example, the Rust compiler can check for memory-safe use of objects on the stack or heap because it has a priori knowledge of those. We strive to extend those compiler checks to all OS resources, such as arbitrary memory regions, tasks, devices, etc. Intralingual design can be broken into two parts. First, matching the OS's execution model to what the compiler expects, and second, using existing language-level mechanisms to implement OS functionality and express the semantics of resources within the strong static type system. First, most compilers expect their output to become part of an executable that runs in one address space and privilege level, such as a program in a user space process. To allow the Rust compiler to view and reason about interactions between all Theseus components, we tailor Theseus' execution environment to match that model. This requires three things: a single address space in which all virtual physical mappings are bijective, or one-to-one. This prevents extralingual aliasing beneath the language level, using something like multiple page tables mapping to the same physical frame. Second, a single privilege level, which avoids having multiple worlds of execution that are unknown to the compiler across multiple builds. And then third, a single global allocator, a requirement of Rust, but this doesn't prevent us from implementing multiple per-core heaps. Now, matching the compiler's runtime model only allows the compiler to view all Theseus components. For it to understand those components and apply its safety checks to them, we have to implement them intralingually. Now, first note that we prioritize the use of safe code above all else, and we only descend into unsafety when fundamentally unavoidable. Instructions right above the hardware, or calling unsafe functions within Rust's foundational libraries like core or Aleph libraries. Intralingual OS design requires identifying the invariants to prevent unsafe or incorrect usage of a resource, expressing the semantics of that resource using existing language-level mechanisms, and then by doing so, we can enable the compiler to subsume those OS and resource-specific invariants into its existing invariants, checking them by default. It also requires preserving language-level context across calls to interfaces, such as function calls. We refer to this as lossless interfaces, meaning that language-level context like type information, lifetimes, ownership, borrow status, that sort of information must be preserved across, for example, the function call. We also this also must be statically insurable. Skip this. We also want to go beyond safety, for example, to prevent resource leakage. We do this in Theseus by implementing custom stack unwinding that's independent of existing libraries, and it works in core OS contexts and with the complicated nature of Theseus' runtime loaded and linked cells. Together with the compiler, unwinding ensures cleanup, as all resources implement cleanup semantics within their drop handlers, and this works even in exceptional execution paths after a panic. This relieves the kernel and the OS at large from the burden of resource bookkeeping. And that's the first benefit of intralingual design. The compiler can take over resource bookkeeping. This means the OS doesn't have to maintain any bookkeeping states for example, in its task struct. So this significantly reduces state spill from all other subsystems into the task struct, since those states aren't needed for resource tracking and resource cleanup, which in turn strengthens isolation. Intralingual design also removes gaps in the compiler's understanding of code because there's no black boxes anywhere in the system. This allows it to approach end-to-end safety from applications to the kernel core, and it shifts semantic runtime errors into compile time errors, much like Rust already does. The third principle is to address state spill, ideally avoid it. The third principle Theseus follows is to avoid state spill. We have a variety of techniques to do so, but the key one is opaque exportation. You can find other details in our paper. Opaque exportation effectively shifts the responsibility of holding progress states from a server to a client, which is only possible in Theseus due to type safety, memory safety, and intralinguality. The server can then be more easily evolved and recovered from faults because it doesn't hold those client-side states. Note that Theseus can still revoke those client-held states, such as an acquired resource or something like that, using its unwinder. As an example of intralingual and state spill-free design, let's look at memory management. In conventional OSs like Linux, memory management subsystems harbor state spill in the form of virtual memory areas, or VMA entries, which must be created, modified, or removed during map, remap, and unmap operations. There is inherent unsafety here, due to a semantic gap between the OS level view and the language level view and understanding of memory, even in existing safe language OSs, which can lead to double free or use after free errors. Extralingual sharing also occurs by mapping multiple virtual pages to the same physical frame, which the compiler does not know of and would thus violate Rust's mutability XOR aliasing rule that ensures memory safety. Our solution to all of this is the MappedPages abstraction. The MappedPages type represents a region of virtually contiguous pages that are mapped to an optionally contiguous set of physical frames. It serves as the backing representation for stacks, heaps, and all other memory regions, such as devices and loaded cells. The map function on the right side here is lossless, ensuring that the caller cannot create an invalid or duplicate mapping because it consumes the allocated pages and allocated frames passed to it. This prevents extralingual aliasing methods, like mapping multiple pages to the same frame, thus requiring all aliasing to occur at the language level using shared reference types in Rust. MappedPages also ensures that its memory region is only accessed safely. It implements all unmap and cleanup functionality only within its drop handler, which is automatically invoked by the compiler or by Theseus's unwinder once no outstanding references to it remain. This allows the compiler to statically prevent use after free and double free bugs. To access the memory region, one must use methods like the asType method shown here, which only allows the caller to obtain a borrowed reference to a type overlaid atop that memory region, ensuring that its lifetime is tied to that of the underlying memory mapping. Obtaining direct ownership of an overlaid struct type is impossible, as that would lossily discard that lifetime relationship and allow for potential use after free bugs to be introduced. In this code snippet, we show how one can use MappedPages for safe access to MMIO devices, namely to access the counter value of the high precision event timer, or HPET device. Of course, the correctness of the HPET register struct layout is unavoidably left to the developer, but the MappedPages design and its invariants ensure that the developer cannot violate isolation no matter how wrong they are. One noteworthy aspect of this is that the MappedPages object on the third line of the main function, mp_pages, is owned directly by the task, so there is no state spill into Theseus's memory management subsystem. But its unwinder can still ensure that the MappedPages object is freed and then unmapped, even if an exception occurs. In summary, MappedPages allows the compiler to check these invariants and more for all arbitrary memory regions, as discussed in our paper. Altogether, the MappedPages type statically guarantees that unexpected, invalid page faults cannot occur. Likewise, there are a host of other invariants related to intralingual task management that enable the compiler to ensure safety and prevent resource leakage and other incorrect behavior in the presence of multitasking. See our paper for more details there. To realize our first goal of live evolution, we employ the fundamental mechanism of cell swapping, a multi-stage procedure that replaces some existing old cells with new ones. In this example, we replace an existing cell C with two new cells, J and K, as shown on the right. While the full details of this procedure are in our paper, in short, this involves loading the new cells in a separate namespace, verifying their dependencies, and then modifying dependent cells to link against the new ones, which requires us to update the stack and perform any state transfer as needed. Many aspects of Theseus' design facilitate cell swapping. For example, the dynamic loader ensures that cells cannot overlap or have their sections interleaved in memory, which makes them cleanly removable. Many other examples are given in our paper. The second goal of availability is realized via fault recovery. Note that many kinds of faults are already prevented by Rust's safety and Theseus' intralinguality, especially language level errors. So we focus on recovering from faults induced by hardware beneath the language level, such as random memory corruption. Theseus takes a cascading recovery approach, in which it first simply cleans up and fully unwinds a task, which allows the system to tolerate the fault, and for other tasks that may depend on the resources shared with the failed task to continue running properly. The second stage is to restart a failed task, which we ensure is completely sound using an intralingual restartable task abstraction described in the paper. The third stage is to completely reload and replace a corrupted cell using the same cell swapping mechanism as before. These recovery mechanisms operate with few dependencies, allowing them to work in core OS contexts like exception handlers. This means that we can recover from more severe and lower level faults than what microkernels can do. Next, I'll give a brief overview of our evaluation, including one of several case studies that demonstrates Theseus' evolvability, our fault injection experiments, and the cost of intralingual and spill-free designs. In this experiment, we show how Theseus can evolve its inter-task communication channel layer, the equivalent of IPC because Theseus eschews the process abstraction. Inspired by microkernel change histories, we evolve an existing synchronous IPC layer based on an unbuffered rendezvous protocol into an asynchronous buffered one. This case study demonstrates several things. One, that Theseus can evolve a fundamental OS primitive that must exist within a microkernel, a kernel API that necessitates joint evolution of dependent user space and kernel components, and a very widely used component, all the while preserving the execution context of tasks that depend upon it. The execution delay imposed by this evolutionary procedure is under a quarter of a millisecond, indicated by the middle two shaded stages in the timeline graph on the bottom right. In this experiment, we inject faults such as random memory corruption into a variety of Theseus workloads, showing that it successfully recovers from just under 70% of total manifested faults. Most of these are due to a lack of asynchronous unwinding support in Rust and its LLVM backend, which we describe in the paper. But some of them, like the 30 failures due to hung tasks, can be handled by complementary hardware mechanisms like watchdog timers. Finally, Theseus' intralingual and state spill-free designs naturally raise questions about its performance. In general, we observe an expected trend in which some state spill-free designs are better than their traditional spill-full counterparts. Many are just a little tiny bit worse, while a small minority impose higher costs. For example, as shown on the left, the MappedPages approach for handling memory performs and scales to many mappings slightly better than the conventional approach used in Linux, which is a red-black tree of virtual addresses linked to virtual memory areas. On the right, we can see that Theseus' safe heap allocator imposes up to a 22% overhead due to tracking allocation metadata in a lossless manner, which associates each allocation with its underlying MappedPages object. On the other hand, the unsafe heap allocator uses raw pointers to ranges of virtual addresses that represent chunks of available or used heap memory. Of course, this is faster, but it completely loses all of the context about the underlying MappedPages and their lifetime. Theseus is not without limitations. For example, it must accommodate some unsafe code, but it strives to detect and prevent dangerous or infectious unsafety with a compiler plugin. We also must rely upon safe language properties for isolation, and thus we have to trust that the Rust compiler and its core libraries are sound. See the paper for a fuller discussion of limitations. In conclusion, Theseus' design specifies a structure of many tiny component cells that are dynamically loaded and linked to ensure their bounds are known at runtime. It follows intralingual design to leverage the power of language and to enable the compiler to check OS-specific invariants and take over resource bookkeeping. And of course, it avoids or mitigates the effects of state spill. Thank you very much for listening. Theseus is currently open source on GitHub, and please feel free to contact us with any questions. Thank you.